Determining the order of a reaction. Say we have a reaction A plus B giving products. And so we know that the rate can be expressed as a rate constant times the reaction of A to some power times the reaction of B, or concentration of B raised to some power. We do not know what A and B are. And generally, we have to find these through experiment. Here's a way we can algebraically solve for A and B, these powers, if we do a couple of experiments measuring the initial rate. Now say we have the following data from experiments. We have the rate of reaction, and that will be in units of, say, molar per second. And we'll have the initial concentration of A and the initial concentration of B for several sets of, say, experiments. This will be experiment number. So, the first experiment, we have a rate of 3.7 times 10 to the minus 2, and our initial concentration of A is 0.1 molar. Initial concentration of B is 0.2 molar. Then for the second experiment, we have a rate of 5.6 times 10 to the minus 2 that we measure, and we've increased the concentration of A to 0.15 molar, and we've kept the concentration of B the same. Now for experiment number 3, we measure a rate of 8.3 times 10 to the minus 2. We've kept the concentration of A the same, but we've increased the concentration of B. Now let's see how we can use this data to determine the powers, little a and little b. The way to do this is take the ratio of the rates for two different experiments. Say I'll take the ratio of the rate for experiment 2. Now the rate constant is K as a constant, so it doesn't change between experiments. So I'll have the concentration, say, of A to the A power, and I'll use a sub 2 to represent the concentration for experiment 2, and the concentration of B for experiment 2. And then I'm going to divide that by the rate for experiment, say, 1, and that's equal to K times the concentration of A for experiment 1 times the concentration of B for experiment 1. Now you'll see first off that since I'm dividing, taking the ratio, that K cancels. And we also see from the experiment, the data, that for reactions, or for experiments 2 and 1, the concentration of B is the same for both, so it's going to cancel as well. So this is going to equal to the concentration of A for experiment 2 divided by the concentration of A for experiment 1 raised to the little a power for both. Now we can write the concentration of A2 in terms of that of A1. So the concentration of A2 is 1.5 times the concentration of A1. Raise that to the little a power. I have the concentration of A1 in the denominator. So now I can break this up. 1.5 to the a power times the concentration of A1 to the a power over the concentration of A1 to the a power. Now the concentration of A1 cancels, and I have R2 over R1 is equal to 1.5 to the a power. So now I can solve for little a here by taking the natural log of both sides of the equation, And noticing that I can use the property of natural logs and write the exponent as a coefficient. And therefore now I've got an a out of the exponent, and I can solve for it algebraically. There. Now I have an easy way to solve for the power little a here. So if I plug numbers in, I'll have the natural log of the ratio of these two rates. So I have 5.6 times 10 to the minus 2 divided by 3.7 times 10 to the minus 2 divided by the natural log of 1.5, and this is going to equal to 1. Therefore, the power a is equal to 1. So now I've determined what the order of the reaction with respect to a is, as first order with respect to a. Now I can do the same thing for the concentration of b. If I look at experiments 3 and experiments 2, I will see that the concentration of A is the same, but the concentration of B differs. Now, I already know that little a powers 1, so I could write a 1 here for the concentration of A, its power, but I don't need to. Now, since the concentration of A for those two experiments is the same, they cancel, K cancels, and now I just get the concentration of B for experiment 3 raised to little b power divided by the concentration of B for experiment 2 raised to its power. Now I can notice that the concentration of B for experiment number 3 is equal to some factor, I'll call C, times the concentration of B for experiment 2. And so that factor C is equal to the concentration of B for the third experiment divided by that for the second experiment, which is equal to 0.3 over 0.2, which is equal to 1.5. So now I can express the concentration of B for experiment 3 in terms of that of experiment 2. So, going back to my ratio of the rates for experiments 3 and 2, this is equal to concentration of B for experiment 3, but I'm going to write it in terms of experiment 2, so it's 1.5 times the concentration of B for experiment 2. All that's raised to the little b power divided by that for experiment 2. So the concentrations of B cancel, and I just get 1.5 to the b power. So again, I can take the log of both sides of the equation. And use my property of natural logs and solve algebraically for B. So plugging numbers in, I get, see, 8.3 times 10 to the minus 2 divided by that for experiment 2 rate divided by a natural log of 1.5, and again B is equal to 1. Therefore, I've determined the power of B. So now I know my rate expression. So the rate is equal to K times the concentration of A to the first power and the concentration of B to the first power. So it is second order overall for the reaction.